Alright, so now you got a basic idea, kind of an intuitive overview of what IFSS is and does, the purpose, the paradigm. And now what I want to do with you is bring you up to speed with the research that we did last semester, or last year, and give you kind of a direction, some of the things that we wanted to do, things that we thought were important, thought needed to be explored. Now, one huge question that was plaguing my mind at the beginning of last summer, and maybe plaguing yours as well, is why fault trees and state charts? I mean, in the intuitive overview, you probably were okay with the idea, get the functional people and the safety people talking to each other, and you'll have a better product. You'll have better safety. I mean, really, you'll have a product designed both to do its function and to be safe, and everybody involved will be talking to each other. Now we do that through the models, but then you get into the specifics. Why does the functional specification have to be a state chart? Why does the safety specification have to be a fault tree? And there are two reasons for that. One reason has to do with just the nature of software testing, and the other reason has to do with the industries that actually use these models. As far as the software thing is concerned, if you're anything like me, when you first came into this, you thought, well, software testing is like beta testing, right? You get regular people to download your program and run it and try it out. Maybe like when they release the new Windows platform, or they release a game on beta. You try it out, but you're a human. You try it and you try to catch things that are wrong, and you'll report bugs when you run into them. But that's only one side of testing, and that's oftentimes quite late in the game. The other side of testing is automated. And when you're dealing with high intensity, safety-driven situations, you want to rely as little on humans as possible. In other words, you want things as much automated as you can. And when you test, as a result, everything is done automatically. You don't go in and manually put in input and manually check output. You specify these are supposed to be the inputs. Maybe these are supposed to be the inputs I give at the interface for the nuclear reactor, so the levels to set for the nuclear reactor, and these are the levels that should come out when it's actuating things in the system. So it's formal, it's mathematical, and it's, again, it's because it's such a high intensity situation. You go into the formal, and that took a little while for me to get my head around. I always thought of testing as just the manual testing that I do on my own applications. You can design something in Visual Studio or design a web page, and you just kind of click through and make sure it feels right. But in this kind of automated testing, you just specify sets of input and output, and you verify that those are what you get, and you run those tests automatically. You generate the tests as much automatically as you can, and you run them automatically, so that once that system is done, there are no doubts that it's going to work properly. You want to get it as fixed and rigid and formal as possible. Now, that's what you do with software. Software, from a functional standpoint, is already that way. I mean, it's a rigid set of instructions given to a computer. Now, safety side, not so much. But with fault trees, that's the closest that you get, generally speaking. A lot of safety is really fuzzy, but we don't want that. We want really, really rigid. This is the specific event I do not ever want to see happen, and these are all the ways that we can imagine that this event could happen. These are all the little itsy bitsy teeny weeny things that could occur on a small scale, and all separate places and situations that could come together to cause this event. That's a fault tree. And a fault tree tries to take what's fuzzy, what's somewhat unknown, and make it as discrete and formal as possible. So, and again, that's what we do. You don't want a rocket or a bomb going off while it's still attached or inside the airplane or the hangar or the base. You want it to go off only when it's supposed to go off. So again, you want to make these things as formal as possible. It's far more important to make sure a bomb doesn't go off than to make sure a game works. So, basics. That's why we go with fault trees and state charts. State charts and fault trees alike take situations that could be kind of uncertain, and it makes them as certain as possible. Now, there could be other ways to do that, certainly, ironically, but fault trees and state charts have a tendency to do that really well. And the second reason I already mentioned, I checked with the fault tree handbook and some handbooks from NASA, as well as with David Harrell, who actually created state charts back in the day. And what I asked them was, what industries use these models? Where are they actually put in practice? And strangely enough, or maybe not so strangely, because again, rigid software is involved, as I already said, it was the same industries. If you go back to our 2011 video final presentation for this project, you'll see one of my slides shows fault trees and their industries and state charts in their industries, and there are like at least 3 industries out of the 4 from each that overlap. So the people that are primarily using these models are in the same organizations. And that's important because we're designing a model for people to use. In a sense, we're designing software for people to use. Just it's not quite to the software point. This could totally be implemented in software. IFSS is so very much a software possibility. But my point is to say, we want to make something that people will actually use. In other research fields, you don't have to worry about that. But when you're dealing with computer science, you want to make something as useful as possible. The reason, at least in this case, what we're trying to do is help current safety testers, current safety engineers work with current functional engineers to come up with a better product, a better way of safety testing. And in order to do that most effectively, we've got to go to the people that are doing this on a regular basis and see, what is it that you use? You use fault trees and state charts? Okay, well, let's see how to combine them. In effect, we want to make sure that whatever model we create is actually going to be used instead of just sitting on a shelf somewhere and never be read and applied by anyone. We want to go out, we want to see how it is they do their thing already, and we want to help them do their thing better. And we can do that best by seeing what they already do and extending it and connecting it with the other team. Now, one really big thing that I did last summer, spent a good portion of my time doing, was finding, to the end of understanding how these things were applied in the real world, finding real world examples of state charts and fault trees. The ideal would have been to find a state chart and a fault tree for the same system or same part of a system. Now, that's somewhat difficult to do as it happens, but it's possible. And you go to the industries that have them if you want to get your hands on something like that. It'll take forever to get your hands on it because it takes so long to go through clearance, but when you're just doing research, they normally are much more willing to work with you. So a lot of my research time last summer was spent gathering real world examples. A lot were kind of space program type stuff, but there were a couple here and there that were different. And we also have a huge fault tree that we put together that is physically assembled. That's a lot more helpful than the virtual file, and that should be wrapped up. It was left in the lab, but Dr. Wong may have moved it and may know where it is. But that that's one of the fault trees that I was able to acquire. Thank God and thank the guy that gave it to me. But the whole idea behind getting real world examples was see how it is that people already use these models and see how we can adapt ourselves to their model and then use their model to accomplish what we already know or at least already think is going to be a good idea, to help them do what they do.